So question 8. Electron diffraction provides evidence for the wave-like behaviour of particles. Electrons are diffracted by a thin slice of graphite. In one experiment, electrons are accelerated from rest through a potential difference of 300 volts, and we've got to show that the final speed v of the electrons is 1.0 times 10 to the 7 meters per second. Okay, so what we need to realise then is electrons have got charge equal to the elementary charge, and if we multiply that by the potential difference they're going through, we can work out the work done on the electron. That work done is going to be going to increasing its kinetic energy, so we're going to get a half mv squared, and if we rearrange this to make the speed the subject, we get 2eV divided through by the mass of the electron, and if we then take the square root, that will give me v. So if I substitute some numbers in, v will equal 2 times 1.6 times 10 to the minus 19 multiplied by the potential difference of 300 volts divided through by the rest mass of the electron, 9.11 times 10 to the minus 31 kilograms, and take the square root of all of that, and your calculator will say 1.0, well, rounded is 1.03 times 10 to the 7 meters per second. Moving on to part B, we've got to now determine the de Broglie wavelength lambda of the electrons. So we'll go with the 1.0 times 10 to the 7 meters per second. So V is equal to 1.0 times 10 to the 7 meters per second, as given in the previous question. The de Broglie wavelength lambda is the Planck constant divided by the momentum, which would be m multiplied by v. So that's going to give us 6.63 times 10 to the minus 34 joule seconds divided by the rest mass of the electron times 10 to the minus 31 multiplied by the v, 1 times 10 to the 7, and that comes out as being 7.3 times 10 to the minus 11 meters. And finally, part C. After the electrons are diffracted by the graphite, they hit a fluorescent screen. The electrons are diffracted because of the spacing between the carbon atoms is comparable with the de Broglie wavelength of the electrons. Figure 8 shows the diffraction pattern, bright rings, seen on the fluorescent screen when the electrons are accelerated through a potential difference of 300 volts. The potential difference is now increased. Explain how the diffraction pattern will change. So what they're going to be looking for with this then is what's going to be happening to the wavelength. So because we know that lambda is equal to h over mv, increasing the accelerating voltage will increase the speed, increasing the momentum, which would lower the wavelength, and if we've got a smaller wavelength coming through a diffraction pattern, that would mean the rings would get closer together. And that's the depth of physics paper completed.